Alright folks, welcome to today's mind-bending episode titled Quantum and the Big Bang. How did the quantum realm forge the cosmos? We're diving into one of the most awe-inspiring topics, the birth of our universe. Buckle up. Did you know the Big Bang Theory suggests everything we see originated from a hot singularity about 13.8 billion years ago? It's like a cosmic fireworks show igniting from a single, tiny point. But what's truly fascinating is how quantum mechanics intertwines with this extraordinary event.
Wait, hold on. A hot singularity? So, everything just exploded out of this tiny point? That's wild. But how do scientists even know that's what happened?
Great question. The Big Bang Theory emerged from Edwin Hubble's observations of an expanding universe. Imagine blowing up a balloon. As you inflate it, the surface stretches outwards. Similarly, Hubble discovered that galaxies are moving away from us, indicating an expanding universe. But when we look deeper into that initial singularity, classical physics kinda breaks down. It's where relativity and quantum mechanics collide. It gets really trippy.
Okay, I think I see it. So we're dealing with two completely different worlds of physics? Kinda like how your grandma's cooking doesn't really mesh with, Michelin star cuisine? Laughs.
Exactly. That's a perfect analogy. You've got your classical cooking solid, predictable principles, but throw in quantum mechanics, which is like an experimental dish that might not even taste like anything you've had before. It's all about probabilities and uncertainties. Quantum mechanics introduces concepts like wave-particle duality. Imagine particles acting like both waves and solids at the same time. It's astonishing.
Whoa, that makes me think a wave could be like a massive surf wave, and the particle is like, a beach ball? They're both there, but in some way, they're totally different?
Right. You nailed it. This duality introduces the idea of quantum fluctuations, which could explain how the Big Bang emerged. Picture a calm lake, disturbed by a pebble dropping into it. That pebble represents these tiny fluctuations that create ripples, or in cosmological terms, particles.
So those fluctuations were, crucial for creating everything we see in the universe today? But how does that even happen? Laughs.
Yes, exactly. The Heisenberg uncertainty principle tells us that in a vacuum, particles can spontaneously pop into existence. It's as if the universe decided to play a cosmic game of hopscotch. In the early universe, these fluctuations weren't random. They amplified into the vast structures we later recognize as stars and galaxies.
Wow, that's such a cool visualization. So instead of building a sandcastle out of sand, you're building it out of, cosmic particles? Us. But then, what's this about cosmic inflation?
Cosmic inflation. It's one of the most mind-blowing ideas. After the Big Bang, our universe went through a phase of exponential expansion, like a balloon being blown up super rapidly. This smoothing of space-time helped explain why the universe appears so uniform today. It was driven by a quantum field, where energy converted into matter, creating everything we see.
Can you explain that a bit more? Where does all that energy come from? Is it like a cosmic buffet or something? Laughs.
You could definitely call it a cosmic buffet. Picture all this energy available in various forms. We just need to decide what to fill our plates with. In the early universe, the intense energy of the quantum field allows particles to be created when needed. As the universe cooled, these particles formed the matter that became stars, planets, and even, you guessed it, us.
That's, mind-blowing. So, is there any evidence that this actually happened?
Yes, indeed. We can actually see the early universe's imprints in cosmic microwave background maps. It's like a snapshot of the aftermath of the Big Bang. Plus, particle accelerators recreate those primordial conditions, And gravitational wave observatories are actively looking for signals from those cosmic events.
That's like having a time machine, right? But what are some of the philosophical debates around all of this?
Great point. Quantum cosmology raises questions about time and observation, like what it means to know something in the early universe. Critics argue that without solid empirical tests, it might be wandering into speculative territory, almost like theorizing a new flavor of ice cream without ever tasting it.
I guess I'd like to think that's a cherry-flavored mystery. And what about the future? Can we unlock these cosmic secrets? Laughs.
Absolutely. Quantum computing is paving the way for simulations of the universe's birth. And observatories like the James Webb Space Telescope are crucial for studying cosmic evolution. The advances we're seeing in gravitational wave detection could even unlock deeper mysteries about early cosmic events.
So, like it's a cosmic treasure hunt. What about the anthropic principle? That sounds intriguing.
Perfect segue. The anthropic principle raises the question of why the universe seems specially tuned for life. Are we just lucky, or does it hint at design, or even a multiverse? Why does our universe have the perfect constants to allow life, like a finely tuned guitar ready for a masterful performance?
So, we could be like a cosmic sitcom, starring all the major players in the universe just to make it possible for us to exist? That's deep! Laughs.
Exactly. And as we explore the interplay of quantum mechanics and cosmology, who knows what breakthroughs await us in our understanding of the origins of the universe? It's a thrilling journey.
Wow! I'm like so ready for more cosmic treasure hunting. This has been absolutely fascinating.